Tuesday, the 31st of January, 2017, just before midnight UTC. A GitLab engineer is rebuilding a broken database replica. They wipe the data directory so it can be copied again. 1 or 2 seconds later, they realize the terminal is connected to the wrong machine. The command is stopped, but roughly 300 gigabytes have already vanished from GitLab's primary database. That should have been recoverable. GitLab appeared to have multiple backups. What happened next exposed that almost none of them could restore the service. This is the night GitLab deleted its own database, discovered its backups were broken, and live streamed the recovery to the world. GitLab.com used one PostgreSQL primary and one hot standby secondary. The primary handled all normal database load. The secondary existed mainly for failover. Git repositories and wikis lived separately. The database held projects, issues, comments, users, snippets, and the relationships between them. One primary, one replica, several things that looked like backups. At about 5:20 UTC, an engineer took a fresh LVM snapshot of production and loaded it into staging for a database experiment. At around 7, GitLab.com came under heavy database load, partly from spam and partly from a background job removing an employee account mistakenly flagged for abuse. By 11, the secondary had fallen so far behind that the primary had already removed transaction logs it still needed. Replication could not catch up. The secondary had to be rebuilt from the primary. The engineer erased the secondary's data and started PG-base backup. The command appeared to hang. It produced no useful output even in verbose mode. Engineers changed replication settings, reduced an 8,000 connection limit, restarted PostgreSQL, and traced the waiting process. What they did not know was that the silent wait was normal. Their runbook did not explain it, and the official documentation did not make it clear. At about 11:30, one engineer decided to clear the database directory and try again. They believed the shell was on the secondary. It was on the primary. The deletion ran for 1 or 2 seconds before being stopped. GitLab estimates that around 300 gigabytes were removed. Now the story should become simple: restore a backup. GitLab listed 4 recovery procedures: daily PG dump backups to Amazon S3, daily LVM snapshots, Azure disk snapshots for some servers, and database replication. The replica had already been wiped. Azure snapshots were not enabled on database servers. That left PG dump and the LVM snapshot. The S3 bucket was empty. The backup job had been using PG dump version 9.2 against PostgreSQL 9.6. That major version mismatch caused every backup attempt to fail. The job did send failure emails, but those messages were not signed for DMARC, so the receiving server rejected them. The backup failed, the warning failed, nobody owned regular restore testing. A green assumption replaced a recoverable database. One usable copy remained, the LVM snapshot taken at 5:20, roughly 6 hours before the deletion. It existed to refresh staging, not as a disaster recovery system, but it was far better than the other snapshot, which was almost 24 hours old. GitLab chose the 6-hour copy, accepting that everything written to the database after 5:20 could be lost. The snapshot sat on slow Azure storage in another environment. Moving it back to production would take around 18 hours. GitLab copied the staging database directory to production at roughly 60 megabits per second. The team also had to recover webhooks separately and increment database sequences to avoid reusing identifiers created before the outage. On February 1st at 5 in the afternoon UTC, the database returned without webhooks. At about 6, final restoration finished, and GitLab confirmed the service was operating. The restored database returned to its 5:20 state. GitLab estimated that at least 5,000 projects, 5,000 comments, and roughly 700 user accounts were affected. Repositories and wikis were stored separately and were not deleted. Some projects could be recreated from repositories, but their issues, merge requests, and other database records were gone. The outage affected GitLab.com. Self-managed GitLab, GitHost, and enterprise customers were not affected. GitLab responded with unusual transparency. The team kept public recovery notes, posted updates, and live streamed the restoration on YouTube. Around 5,000 people watched at the peak. For several hours, database recovery became YouTube's #2 live stream. Transparency did not restore the missing data, but it let users see the uncertainty, decisions, and progress in real time. The command was the trigger, not the root cause. Replication was not a backup. Snapshots were missing or too old. Logical backups failed. Failure notifications were rejected. Restore procedures were not regularly tested. No one owned durability. GitLab rejected the comforting answer of simply making the delete command safer. Its postmortem says the ideal environment is one in which you can make mistakes, but easily and quickly recover from them with minimal impact. A backup does not exist because a job ran. It exists only after somebody has restored it. GitLab changed backup monitoring, increased snapshot frequency, improved runbooks, and assigned ownership for data durability. The engineer noticed the mistake in seconds. The system took 18 hours to recover because every layer behind that human had already failed. This is postmortem, one failure per episode, rebuilt from the primary sources. Primary source: GitLab's postmortem of database outage of January 31st, published February 10, 2017.